So you will be actually, writing your weight estimation report and, calculating. Your presentation. Hello, are you able to hear me properly?
Yes.
Okay. I'm hearing a lot of echoes. Just to give you an idea of, what the first time you're writing the report, so you may be at a loss, what should a report contain and things like that. You can present in any form you want. I'm not talking here about the presentation, but about the report. So the report should contain first your mission profile, what mission profile you are taking, you have chosen. Then fuel weight fraction for each component of the mission. So this is be going into the details of the second one now, fuel weight fraction. So section 2.1.1, you should mention what is the takeoff fuel weight fraction you have chosen. 2.1.2 will give you climb and accelerate if you want. If you want to accelerate, there is some a figure given. You have to accelerate to cruise speed most of the time. But there are some exceptions. Okay. So you choose the Mach number and value chosen. Then 2.1.3 for cruise, use the Brigade range equation. So the following should be clearly mentioned in the report. I am telling this because if you do this, you will learn something, okay, and also demonstrate that you haven't made any mistake in this choice. Commonly made mistakes. This is a commonly made mistake. That is why I am going through so much of, pain to tell you where you'll go wrong. What is marked in red is where you should be careful. Now, aspect ratio, assume from comparison aircraft relevant data. You may need this for some of the calculations here. Then maximum L by D ratio you chose from figure 2.4 any other means. So L by D is chosen as 0.94 L by D max. Now, if you want to modify it based on winglets, etc., go through this section. Mention all these clearly in the report. What you have done for your aircraft. Then you have to assume a value of SFC or TSFC. Now you have to clearly mention the value and units of C or C hat. Then units of velocity or range used in the range equation. You have to mention what units you are using for each of these parameters. If necessary, assume the value of wing loading only for this from the comparison aircraft if it is needed. Okay. If it is not needed, you don't have to assume this. Because you will be estimating in the next stage. If you need it in this stage, you have to go from historical data. Don't worry, you don't have to come back and change this again if your wing loading is different later. Don't do that. You'll go into your infinite loop if you start doing that. So this is just to get an initial weight estimation. So you can assume a reasonable value of wing loading here if necessary. So if applicable, you can use table 2.2, which we saw last class. Now what you have chosen, you should mention clearly what you have chosen. Well, I have the book, so I can actually, have the whole table. You don't have to reproduce the table there, but you say that from table 2.2, I have chosen this value for this. If you can justify why you have chosen that value, use the justification. Because remember, when you go to a, say, VC, again, I always choose VC because they are the ones who have the money and you have to convince them. They are free to ask any question they want. So if you mention why you have chosen something clearly, that will be a better report. You can give reasons for each and everything which you have done, your actions, most of them. Then you'll be in a in a good position to talk to anyone about this. So most important thing, mention the units of the variables you use in the formula and show the calculation for this. How you have calculated, you show this. This is important because this is where you may go wrong. If you go wrong in this, probably the entire design you may have to redo later, starting from this point. Okay. So please show these clearly. If possible, if you finish it before the presentation, then show this in the presentation itself. Then acceleration to high speed, important for racing aircraft, fighters, interceptors, etc. Use if it is applicable for you. If it's not applicable for your design, you don't have to use this. Then you have to clearly mention what you have done for your aircraft. Then there is a section for combat. Use it only for fighter bomber if there's a combat section. Two point 1.6 actually descent, I think. Then 2.1.7 is what is 2.1.6? I'm not sure. You just go through that yourself. 2.1.7 is 2.1.6 is second cruise. Okay, second cruise for some of these fighters and bombers, and their L by D may be different, velocity may be different, and weight may be different. So you have to carefully, look at 2.1.6. There may be a second climb also. So mention all this clearly. Then 2.1.7 is loiter at maximum L by D. So you loiter not at 0.94 L by D, but you loiter at maximum L by D, if applicable. Then mention units of the variables used in this formula also and show the calculations. Okay. Then landing is similar to takeoff. You can refer to them. Then mention whether you use the graph or the formula for estimating empty weight fraction. Clearly mention graph graph number so much from this book. I'll appreciate if you do the reference also properly at this point of time. How do you cite the reference? You may cite this book, Thomas Cork, the end references. Which style do you use? You mention. You may use IEEE style. There are so many styles of references. But use one correctly. I want to see whether you can refer this properly. It will be very useful for your project. Okay, when you go to your final year project, this knowledge is going to be very useful. I will suggest, you can go through IEEE citation format right now. Or you can use other methods of reference. Standard methods. Don't refer in your own way. Okay. You can say that I have all the information there. What more do you want? No, you have to refer it in a proper format. So you find out a proper format and refer. I'm giving IEEE only as a guidance, but you may find so many other formats and bring it to our notice, maybe during a presentation. So then you can also say what is the initial takeoff weight you assume for the iteration. For the first iteration, show a numerical calculation so that, if you're not using a program, you are doing it manually. Show the calculation. Even if you are using a program, manually calculate the first iteration and check whether the program is also giving the same value. Otherwise, one of them may be wrong. Okay. Then you can use the program to, for the subsequent iterations. Then mention how many iterations it took to converge. For some designs, if your guess value is very near to your weight, It may converge in less than 10 iterations. For some, it may take hundreds of iterations. So it depends on your design and where you start, whether your starting value is near to your just assumed value or it's very far away. And if you have any issues, mention, sir, it did not converge, diverging. What's happening? Something wrong. If I change something, will it converge? If you have issues, you note the issues and let me know. Okay. So before I forget, I'll just share it with whom shall I share it with? Sanjay?
Yes, I will share. I'll share to the class.
Okay. See, just to set the expectations, no, so that you don't make too many mistakes. And then, to be honest, I'm trying to make my life easier. Okay. Sent you.
Received, sir.
Yeah, thanks.
Thank you,
Thanks.
sir.
Welcome. So, shall we? Now, since I've finished what I wanted to say, it's time to ask now who is this? Priyadarshini. Priyadarshini. Is Priyadarshini there? So, if she's not there, let me go to the. Yeah. CB. CB.
Yes, sir.
Just say something, tell something, or usual break here.
Yeah.
Hmm. So
What?
this is you should always read a joke before you come to the class. Okay. Yeah.
Should I
Tell
say like anything, sir?
anything what you want to say. Just share. Yeah. General knowledge for all of us, whatever it may be.
General knowledge.
No, I don't say that you should say general knowledge. You can tell a joke. You can tell something about yourself. You can tell whatever you want for just for a break. We want a break, and you are the right person chosen today.
Okay.
Tell. Hmm.
It's actually very cold outside, sir.
Where are you? Where are you?
Coimbatore.
I'm. It's cold. Huh? I'm in office. It's not so cold actually. It's
Yeah,
pretty warm, but it's a lot of rain. I mean, I can see a lot of clouds near the
yes.
mountain.
It's actually very sunny outside, sir, but the
Huh.
atmosphere is cold.
Oh,
You feel
wind effect.
like it's
Probably the wind can make you feel cold.
okay.
Which
Like
which part of which part of Coimbatore are you in?
I'm near Sulu, sir.
Okay. That has a probably different kind of climate from Madurai. You say.
Like it is too cold that sleepy, sir.
Oh, interesting. Is your house? A lot of empty space around your house.
No, it's like it's covered by trees, sir.
Okay. Good. So whenever you look at the temperature, they will say due to wind, the temperature, is dipping or increasing. If you go to the timeanddate.com, have you gone there?
No, sir.
I think we'll find now time and date. 518.com. Are you able to see my screen?
Yes, sir.
Okay, Coimbatore, 10-7. There's the time zone map, weather, weather, current weather. Pilamedu, 24 degrees centigrade, but feels like 23. So wind, 11 kilometer from southwest. Forecast maximum maybe 32. So 23 may feel cold to you if there is a wind. These are all, something which is very statistical, correct?
Yes, sir.
Statistical things only give you an idea. They don't tell you the real thing.
Yes, sir.
That reminds me, I just, when you talk of statistics,
Okay.
yeah, I'll say use it in some other time. There was one lady, I think, I read in some WhatsApp. If someone else also received and read that WhatsApp, you can tell me the names and figures if I'm wrong. There was an old lady, old. She finally, she lost her children, husband in France. So she was alone, and she was around, going to be in 80 or 90. She had a house. So
Okay.
one man told, okay, he made a agreement with her. He'll pay you some money upfront. He was around, 40 or something. So he told, I'll pay you for 4 years, your whatever you want, your living expenses per month. I'll give you so much money. Hmm?
Okay, sir.
So he made a deal. Based on statistics he made, because statistics told that average lifespan of people in France is 85 or something. She's already 84 or something. Hmm? So he calculated probably 1 or 2 years I'll get the house at very cheap rate.
Okay.
So he made the deal. Then I waited, waited. 10 years rolled by. She became 94, and he became, some 50 something. 10 years, he became 60. The lady became 104. Okay.
Yes, sir.
Then this man passed away. Okay. And then his children had needed some. If they don't honor that, they won't get the house. So they have to honor the will to get the legacy, that house or something. And she went on to live till 120 or 130 years, and on record she became the longest
Long.
living, the person or a woman who lived for the longest time in the world till that point in France. 1700 it happened.
Oh,
Okay. In between, I think she acted in some drama or something, and she got some money there also.
okay, sir.
So finally, because this poor fellow, believed in statistics, hmm,
Yes,
he
sir.
lost a lot of his money, and his descendants, finally after a lot of paying a lot of money, them also they got hold of a house which was divided into so many divisions by that time.
Yes, sir.
So just to tell you that although we believe statistics in our aero design, hmm,
Yes,
if you
sir.
try to apply it to individual case, it might
Fail.
backfire. It might backfire. Okay. So
Okay, sir.
this is statistics. So what you see here is actually 23 degrees, but right from you we know it's cold.
Yes,
Hmm?
sir.
Good. Nice break. Thanks, Siddhi. Thank you.
Thank you, sir.
Okay, actually the next exercise will be wing loading. Mm, You'll be going to wing loading till Tuesday, because Wednesday you have your this one, no? You have your presentation starting, okay, for weight estimation. So it is good to know what to do after that. Some of you may finish everything fast and you want to, go to the next one quickly. So that's good. I encourage that. So I'll let you know what's the wing loading about. Hmm. Basically, we need to, there are so wing loading depends on many factors. Some of these are given here. So wing loading effect on takeoff distance is affected by wing loading, landing distance also, and climb rate is affected by wing loading, acceleration is affected by wing loading, range means actually it is the cruise speed is affected by wing loading, combat is also affected, your ceiling height is also affected by wing loading, then glide rate. Some of main points are given here. So now table 3.1 will give you 3.1 will give you some general wing loading in terms in British units, pounds per feet squared. We'll be looking at Newton per meter squared in our calculation. Don't worry if your answer doesn't fall within this range because I might have given some crazy parameters. So this is just to give you an idea. Don't take your answer from these. Okay. So wing loading is defined as W by S. S is wing platform area. And wing loading will affect all these, as we have seen all these parts of a flight plan. Now, suppose you design a wing loading, you choose a wing loading that optimizes one of these parts. For example, you want only for cruise or range, you choose your wing loading. For example, long range commercial aircraft traditionally have a higher wing loading maximize their range, whereas combat aircraft tend to have lower wing loading to provide better maneuverability. So combat aircraft, the range may be affected. For long range commercial aircraft, the maneuverability may be affected. Okay. So you have conflicting requirements here. You have multi-purpose aircraft, more than one principal mission, sometimes require compromises regarding wing loading selection. So you may have to think of something new, like our MiG-23 aircraft in the hangar. It has variable sweep, so it has a larger area or larger wing loading during takeoff. Sorry, smaller wing loading during takeoff and larger wing loading during climb and cruise at high speed. So table 3.1 gives various values, but even the lowest of this, which is high altitude aircraft, 45 plus or minus 15 pounds per feet squared, has a wing loading 25 times higher than the Gossamer Albatross. What is the Gossamer Albatross? Human powered aircraft. Okay. Can I give human powered aircraft design to any one of your groups? I don't think so. I missed out this time. So you see a very huge, very large wing. So you can see that the aim of this is different from any of these aircraft. Now we look at this, look at these things in detail. Okay. So wing loading effect on takeoff. Now we all know, just you remember the definition of CL, it will solve a lot of problems for you. CL is L by half rho v squared S. Most of the time we'll approximate L is equal to W. There are times when we don't do that. Okay, L is probably some load factor times W sometimes, NW. For this, we can approximately say lift is equal to, same, lift is equal to weight. So, if we invert the equation and solve for velocity, you get V is equal to W by 2W by rho S CL the whole power half. Now, for the stall speed, corresponds to the stall CL. So CL max is the stall CL. Corresponding speed will be stall speed. And this will be the lowest speed possible. You cannot really fly below the speed, whatever you do. So CL max is the maximum 3D lift coefficient for the aircraft. So later we look at methods which actually increase the CL max. Chapter 9, very long way down the road, high lift devices. There we look at how to achieve the CL max and how to actually estimate the 3D lift. Right now we'll do the following approximations. We'll assume that takeoff weight is equal to 1.2 times the stall takeoff velocity is equal to 1.2 times stall velocity. Okay, there are okay, for some it may be 1.1. Right now we'll assume 1.2. So you substitute this velocity for V takeoff. You get something involving wing loading. Okay. Right now we look at very approximate estimates. You'll always you will calculate the takeoff distance more accurately later. It may be sometimes significantly different from what you assumed here, but you don't have to worry about it now. Okay. So we wish to demonstrate the influence of wing loading on takeoff distance and get the first estimate of the takeoff distance. So we don't, although this 3.2 is given here, we are using another empirical method to estimate takeoff distance. For this, we use historical data on the takeoff parameter TOP, which has been found to correlate the takeoff distances for wide range of aircraft. Now, this TOP is defined as wing loading at takeoff into 1 by CL max into W by T. W by T is 1 by T by W. T by W is an important design parameter, thrust to weight ratio, just like wing loading, to 1 by sigma. Sigma is your takeoff airport may not be at sea level height. It may be at some height. So the density ratio at that height is known as sigma. All right. Now you have a formula like this. STO is 20.9 to takeoff parameter into this one. All those stuff. You should keep it in mind that this T by W is non-dimensional. So 1 by sigma is non-dimensional. I mean, it is also non-dimensional. CL max is non-dimensional, but wing loading has a dimension. Okay. Why is T by W non-dimensional? Abhishek? Abhishek?
Yes, sir.
How can I say T by W is, how dare I say T by W is non-dimensional? Does it have dimension or not? T by W. Thrust, let's say in newtons. Then weight should be in kg. How is it non-dimensional? Weight also should be in newtons. So it's mg. Okay. You understood? Abhishek, do you understand?
Yes, sir.
Yeah. So weight should be in Newton, thrust is in Newton, so T by W is non-dimensional. But then, you see, to use this formula, you are having this 20.9, 87, etc. Yeah, that's okay. Thanks. You can mute your mic, Abhishek. Thank you. If you want to use this, you have to. It is telling the coefficients of units foot per pound per foot square. So to use this, when you evaluate this TOP, this WIS should be pound per foot square. Okay, remember when you want to use this formula, we should use WIS in the pound per foot square. Finally, when you present, you will do it in Newton per meter square. That is one important thing to remember. When you make mistakes with these units, the small error will, manifest itself as a huge mistake later sometimes. So be careful. With that, you evaluate takeoff parameter and then you use this formula. So S takeoff should be in feet. Okay. So you can look at this graph for the units. Wing loading is 174 pound per feet square. S takeoff is feet. It's in feet. Feet by 1000 is given. When you do this, you'll know whether it's thousands of feet or feet. If you get a number as 1, that means it is actually 1000 feet. So this is another graph is given as on x-axis you have CL max, on y-axis you have STO. It is plotted for various value of T by W. Okay. So you have to draw graphs like this. T by W is 0.4. When you increase T by W, the takeoff distance comes down. You see, it should logically agree. 0.4, 0.6, 0.8, 1.0. If you have more thrust, you can take off faster. Physically, you should be able to reason out these graphs also. Otherwise, something is wrong in your graph. So two parameters that can be used to control the takeoff distance are thrust to weight ratio T by W and maximum lift coefficient CL max. So you may have to assume these things initially. Okay, the curves correspond to the effect of CL max. You don't even need to assume anything. So it's given for CL max for some type of aircraft. Generally, it is given like this. Okay. At this stage, you can plot something like this for aircraft, but what is more important, you have to make a plot like what I'm going to show now. That is known as constraint diagram. We'll be building up on that. Okay. So you can actually draw a graph with wing loading on x-axis and T by W on y-axis. Okay. So for takeoff, you may get, something like this. Now this may be for, say, yes, takeoff is 4,000. Maybe this may be for yes, takeoff is 2,000. Something like that. Okay. So you can plot for various yes, takeoff. Then for fixed, for example, let's take off 2000 itself. You can put this as for CL max. You assume from the table. You should choose something else. You have to draw this graph also. Okay. And suppose if S takeoff is 1000 or something. 5,000, something like that. Okay. Suppose S takeoff is 4,000. That is what. Suppose there is a constraint on that. You are taking off from Mumbai aircraft that has a limitation of 4,000 feet runway length. So you can take around 70% of that, which is 2,800 feet. So you write draw something for 2,800 feet also, 2,800 feet. In here 2,000. Then what you do is the one which is relevant to you, you give it some red color or something. Okay. This is what you want. Later on, if you want to change this length, this will tell you which direction you should go. Should you go this way to change your thing, or can you go this way? So better make this kind of plot. Okay. Clear? What on x-axis? Wing loading. What on y-axis? E by W. You can make plots like this. Some people, the STO may be fixed. They can make the same graph with CL max. So they will have some other graph like this. So this is for people for whom takeoff distance is not specified. Okay. You can choose the CL max and do that. If takeoff distance is specified, for example, okay, you can actually make both the graphs. Because if you want to change the specification later, you can show this graph and argue. So now fix the STO. Now takeoff distance should be less than 1,000 feet. Something I'm giving you. Less than 300 meters or something. Somebody will have some restriction, or should take off from this runway. So this restriction may be there. In that case, you plot this for say CL max is 1. Maybe CL max is 1.2. CL max is 1.6. You plot such curves. Okay. I don't know right that it look like this or it move like this, but you just plot these for various values of CL max also. So plot these two curves. And the red one you mark what you have chosen, what you think it will be correct. Okay. Things are clear so far, or any confusion? Divya pages clear?
Yes.
Yeah. Okay. So Divya pages, tell something now.
Sir, what's it?
Tell something.
Sir,
Anything you want to share? Yeah.
currently I'm reading Fall of Giants book, sir.
Again? Huh?
Sir, I'm currently reading Fall of Giants. It's a book by
Fall of
Ken.
James.
Yes, sir.
Book by
Ken Follett.
Ken Follett. Wow. Okay.
Yes. It's about how World War One happened and what are the decisions made, like that.
How
How
what is
World
it?
War One happened.
I don't get you. How?
World War One, sir.
World War One. Oh, double. Okay. World War One happened.
Yeah.
Okay.
And what are the big families involved in it, like that.
Oh, okay. Ken Follett. That's news to me. I know he's a very good author, but if time permits, I'll try to read that book. Good.
Yes, sir.
Okay. Okay, thank you.
Yes, sir.
So let's landing also will have is very similar to takeoff. Okay. Only difference is there's a landing parameter which has only wing loading into the take into consideration. Mm, landing may have some problem. Okay. Some people have experienced some issue with this formula because it's again a statistical formula. Okay. But anyway, you try your luck. Try to draw the same kind of graphs. Okay. For as you did for takeoff. So equation 3.7 indicates that shorter landing distances can be accomplished by a combination of lower wing loading at landing and a higher CLmax. Both of these make sense. Okay. Landing parameter will be less if wing loading is low or your wing area is large. We have high CLmax also, landing parameter, landing distance will be less. So both of these make sense. So usually, if you cannot get correct what you want from this, we use a very high CLmax for landing. This we achieve by using flaps and slats. So you do this is something which we can fiddle with. What I am telling is, if we can actually change these using CLmax and uh, probably we can change the geometry during landing. We want a smaller landing distance. Anyway, you plot very similar graphs to your takeoff or landing also. Okay. Like what I want is wing loading on x-axis, T by W and y-axis. Using this, how will you do that? There's no T by W because your thrust is switched off here. So this won't really, you assume a T by W. Okay, for your wing loading, the T by W is always 0. Any wing loading you take. So there is no sense in drawing the diagram for landing. Okay, so just that you estimate this and keep it ready. You can do the other plots, CL max versus landing length, what he has shown. Okay, so we'll kind of stop here today. Tomorrow is a holiday, if I understand right. Is it non-working Saturday, right, Sanjay?
Yes, sir. Non-working Saturday.
Okay, so we'll meet on Monday morning. So I want to do this because when you finish wing loading, you shouldn't say, sir, what to do next. You will already know what to do. You can go to the next exercise if you finish wing loading. That is why I am slightly hurrying now. I may not be very kind on the later parts because I will ask you to read things yourself. Have doubts, you ask me. Okay, so now we can stop recording, Sanjay. I will take attendance.